Good morning. We are headed in now to chapter 16. We're going to be looking at sound. This is the last chapter. It's our last chapter for the Physics 4A course. And it's a continuation of looking at waves. So in chapter 15 we said that waves were a disturbance that propagate through some kind of a medium, and that the wave really consisted of some kind of a synchronization along the different locations within the medium. And that's the same thing with sound. And so now when we talk about sound, we're usually thinking, here are the topics that we're going to be looking at. When we look at sound, we're usually thinking in terms of something we hear. So we'll talk more about that. We're going to start off looking at some different speeds at which sound propagates. The one that we'll probably be using the most is the speed of sound in air. How fast do mechanical disturbances propagate, these longitudinal waves, propagate through air? And at 20 degrees Celsius in one atmosphere, it's about 343. You can notice that at lower temperatures, speed slows down. The speed of sound slows down. It's a lower value. And then you can also see that as we get into materials that are more substantial, let's see what we have here. We've got the speed of sound in water. You can see when we've got a low density gases, the speeds go up, like hydrogen and helium. You can also see that in water, ocean water, the speeds go up. And then in very rigid materials, steel, aluminum, glass, the speeds are in the thousands of meters per second. Now there is there's kind of a saying that if you are in a lightning storm and you see the lightning, you can count to 5, or you can count until the thunder arrives. For every 5 counts, it's 1 mile for every 5 seconds before the thunder is heard. And so what this makes use of is the difference in speed between light and sound. Now light's not a disturbance in a medium. Light is a collection of photons traveling at really high speeds. So I know a lot of times light and sound are presented in terms of their similarities, and I actually prefer emphasizing their differences. So we do have sound is a wave. It's a disturbance propagating in a medium. It does turn out that for light, we can talk about things like wavelengths and frequencies, the same as we do with sound and with waves. But with light, those properties are associated with the particles, the photons, that the light's made out of. In any case, let's take a look at this example. Now, a mile is 1,609 meters. So the time that it would take light to travel a mile, we can take the distance, divide through by the speed at which light's traveling. And light goes really fast. And so what's happening here is it's just, 5 microseconds. So for our purposes, that's like saying no time at all. The light's there almost instantaneously. Whereas for sound is a disturbance propagating through a medium. In this case, the medium is air. And the velocity there is 343 meters per second, which sounds pretty fast until you compare it with light. And this works out to be, 4.7 seconds, so not quite 5 seconds. But yeah, the 5 seconds per mile rule works pretty well for the delay of the thunder. So as the lightning passes through the atmosphere, that creates a disturbance. That disturbance propagates away from that location, and we hear that as thunder. So here's some of the characteristics for sound. The loudness of the sound is related to something that we call intensity. Now, we introduced intensity in chapter 15. So last chapter we introduced what that was. It was energy per time per area. And so the loudness, as the intensity goes up, we experience that sound as being louder. Pitch. Different pitches are related to frequency. So we have really low pitches, and we have really high pitches. So we have a range of different pitches, and we find that those are directly related to the frequency of the sound. Now, in terms of frequencies, human hearing is considered to run between about 20 hertz and 20,000 hertz. So that's the range of pitches that humans are able to hear. And then the upper limit decreases with age, so I'm guessing I don't hear all those high frequencies anymore. You guys probably still do. Now there's ultrasound, so we're not, even though our hearing is limited to that range of frequencies, if the frequencies go higher, they still exist. We can generate frequencies that are higher. It's just that our hearing system is not set up to pick up those higher frequencies. And then there are lower frequencies below the 20 hertz, high frequencies above the 20,000. Here's another example. It's an autofocusing with a camera. It says that cameras can use ultrasound as a way to autofocus. So if I've got a camera out and I'm not paying attention to how it focuses, if it's on auto, then somehow the camera is determining which object I'm trying to take a picture of and how far away it is. So if I hold my camera up and ready to take a picture, ready to take a photo, what's going to happen is for these cameras that they're talking about here, the ones that are using ultrasound, it's going to send out an ultrasound pulse, and then it's going to time how long it takes to reflect and come back. So for this, what we can do is we can take, I think this, the object in this case was 1 meter away. Yeah, 1 meter and then 20 meters. Okay, so here's the camera, here's the person taking the picture. The ultrasound goes out, bounces off that really handsome person over there, and comes back over and is picked up by the camera. So the total distance traveled in this case is 2 meters. 2 meters divided by the speed of sound gives us 5.8 milliseconds. So if I have an auto-focusing system based on ultrasound, the system has to be able to identify times as short as, well, in this case, 5.8 milliseconds. What if they're 20 meters away? Well, that's going to take 20 times as, that's going to be 20 times the distance. That makes that 40 meters divided by 343. This works out to be about 1/10 of a second. Okay, so it's pretty quick, right? If you're taking photos of things, it's still pretty quick that the ultrasound would go out, reflect, and come back. Now, the sound that we have in air and in water, in gases and liquids, consists of regions of compression and then rarefaction, or regions where the air is more spread out, regions where the air is compressed. Now, we saw this also in chapter 15. We called these longitudinal waves. And so the wavelength is defined as the distance between one compression and the next. Now, these can be represented in terms of a displacement variation. So what's happening is individual molecules of air are moving back and forth. As the wave goes by, what happens is the air molecules get pushed one way and then they bounce back, and then so you've got this oscillation going on as the sound is passing through that region. And what that does is it creates regions of compression and regions of rarefaction. Now, this is, here they're using a graph to show a sine function showing how the displacements vary. Now, what would that mean? It would mean that all the air molecules, when the sound is not passing through, the air molecules are lined up uniformly, roughly, along the x direction. But that, what happens here is that, well, let's look at this region right here. I've got some of the air molecules that currently are shifted to the right. And then I've got other molecules farther downstream that are shifted to the left. And that would be a location of a compression right there. Now here, if I look at this point right here, this, at this region, I've got air molecules here that are shifted in the negative direction, so they're pushed to this side. Meanwhile, air molecules that were located right next to them have been pushed to the right. So that would be a rarefaction. This would be another compression. So that's kind of the way that you can read this. And then what we can do is we can make the matchup with a pressure plot. And we'll see how these formulas work. We'll look at some of the derivations of how the displacement formulas, the displacement amplitudes are related to the pressure amplitudes. And you can see from this graph and from our discussion that they're shifted by 90 degrees. So now the numbers that they've given here, notice that the difference in pressure, when I have sound passing through, there are going to be these pressure variations, these pressure compressions that get set up. And this is at 1.002 atmospheres, so it's fluctuating around 1 atmosphere, and it's fluctuating by a small amount. It's fluctuating by about 20 pascals compared with 100,000 pascals, which would be 1 atmosphere. And you might think, well, that's a pretty small pressure variation. Can you even hear that? And not only can you hear this, this is a really, really loud sound. This is something that would be at 120 decibels, would give us the plots that we're seeing here. So the displacements are small, the pressure variations are small, even for loud sounds. So here's kind of a derivation of what's going on. So let's say we've got this region of air. You can see this compression region here. There's another compression region right here. What we're going to do is we're going to take a cross-sectional area. Now remember, we're using S as a cross-sectional surface area here. And so I've got a region of space. So this delta X represents a small region of space. And then the delta D is the amount within that region of space, how much has the air been compressed? So how much has the boundary of the molecules that typically would have been in this volume, now that the wave is coming through, how much of those molecules been compressed? And that's being called delta D. Now D, if you remember from chapter 15, is the displacement of the medium as a function of position. So D varies as a function of X. Now here, they're going back to actually chapter 12. We get to use all the chapters from the course here because it's the last chapter. So pressure differences can be related to the bulk modulus, and then what we're going to find is it's the variation of the displacement compared with the variation in length. So let's take a look and see how that, well, here's the rest of the formulas. So here are the formulas that they've derived, saying that the variations in pressure then are going to be a negative cosine. Here is the traveling part of this wave of the sound. This is the bulk modulus. This is the amplitude of the, how much are the air molecules shifting back and forth. And this is the wave number. Now, we can take the formula for the bulk modulus and write that in terms of the speed of the wave. And we can take the wave number and we can write that in terms of omega and the speed. So let's see what this is going to look like then. So going back to that picture that we had, here is the formula from chapter 12, looking at the bulk modulus. That's in terms of delta V over V. Now for the object that we've come up with here, V, the volume that we're looking at, is S times delta X. So here's the delta X, here is the cross-sectional area. The delta V, the amount that the volume has been compressed, is the cross-sectional area times delta D. What's the value of displacement compared with the size of X? So what we can do, if you remember, this is referred to as strain. When I take a certain volume and I compress it, the delta V over V is called the strain. So how much strain is the air under? And that's going to be delta D over delta X. And in differential terms, we can write that as the partial derivative of the displacement with respect to X. Now, remember back in chapter 15, we were writing the displacements as sine functions. We found out that the sine and cosine functions are solutions to the wave equation. So it predicts the existence of displacement waves that behave as sine functions. So to take a derivative of that, if we take a derivative with respect to x, that's going to bring out a factor of k. So Ka cosine kx minus omega t is the derivative. Taking that, plugging it into our formula for the bulk modulus, gives us a pressure variation. This is the same formula they ended up with. The pressure variation of the bulk modulus times the wave number amplitude of the wave, and then the cosine of kx minus omega t. So we kind of filled in some of the steps there. I felt like they had jumped through those. Now, there's a couple other formulas in use here. One of these, and we'll get to these in a few slides here. This one we've seen from earlier chapters. The speed of the wave is given by omega over k, the frequency over the wave number. At least that's one relationship. But as we're finding in chapter, I'm going to say 14, 15, and 16, there's a lot of formulas relating all of these variables that we're working with. And so we have to sit down and go, does that formula work too? Because I've seen other variations of this. So this is how these are related. And then here, the bulk modulus and the density of the air are going to determine what the speed of the wave will be. Okay. So again, these are things that we've looked at in chapter 15. So we're going to substitute those in. What we're going to do is use those two equations, solve for B, solve for K, plug into this formula, and substitute. And what that leaves us with is a pressure formula, pressure amplitude formula. The variations that we see in pressure are going to be given by rho times omega times the speed of the wave times the displacement amplitude. So we've looked at displacement amplitudes in chapter 15, and now for sound we're going to relate those to pressure variations. Now back in chapter 15 also we had derived this formula saying that the intensity of a wave, 1/2 rho omega squared, a squared times the speed of the wave. And now what we can do is say, well, that the intensity formulas that we solved in terms of cross-sectional area, those now can be written in terms of pressure variation. So I can take the formula we've derived here, solve for A, which looks like this, take this, plug it in, now that's A squared. So I'm going to get delta P squared over rho squared, I'm going to cancel one of the rho's. Omega squared is going to cancel the omega squareds, and V wave squared, cancel one of the waves. So this is the intensity in terms of displacements, amplitude, and this is the intensity in terms of pressure variations. The delta P here is representing the maximum value, the maximum pressure variations that we see. So it's a pressure amplitude versus a displacement amplitude. We can write the intensities either way. So those are going to be handy formulas to have. Here's the way they've written it, which looks like how we've written it. Again, I'm emphasizing this is the speed of the wave, not the speed of individual pieces of the medium, not the same thing. And then I've used omega instead of f frequency. So there's factors of, a couple factors of 2 pi that go along with that. Other than that, everything matches up. So that's the way they've done the calculations, and they look pretty similar. All right, let's talk about how loud sound is. We can measure that in terms of intensity. We can measure that in terms of some number of watts per square meter. Now, when we do measure intensity in watts per square meter, what we find is that there is a threshold of hearing is what we consider this. What are the faintest sounds that we can hear? You know, when you go and you do those sound tests at the doctor's, and you go into that room that's really quiet, and you put on the headphones, and they start playing the sounds. You know, they say, you know, hit the clicker every time you hear a sound, and they get fainter and fainter, and they go really low, and they go really high in pitch. They go back and forth. So they're mapping out your hearing in terms of frequency and in terms of loudness, in terms of intensities. Now, we can hear all the way down to intensities of 10 to the minus 12 watts per square meter. And that's just astounding. So that is saying, let's say that I'm standing here and I've got sound coming towards me and I'm listening, and if I take my square meter, which every physics student carries around with them, so here is my square meter, and if I take just 1 joule of energy, of sound energy, that passes that 1 square meter boundary every second, 1 joule of compressional energy, I can hear that. It seems like that's just such a tiny amount of energy. There's no way we would hear it, but we do. And in fact, let's think about this. My ears are not, you know, 1 square meter in size. They're much, much smaller. So each second my ears are taking in a tiny fraction of this 10 to the minus 12 joules that comes through that square meter. So anyway, sound, you can hear just a tiny amount of energy that goes into sound. Now what you might think is, well, wait a minute, what about the air molecules themselves? How much energy is in the air molecules? And it's much, much greater. So when sound passes through air, the additional energy that is there due to the passage of the sound wave or the compressions is a tiny, tiny fraction of how much kinetic energy is already present in the air molecules. Okay, so it's again, it's a slight variation in displacement, it's a slight variation in pressures, and it's a very slight variation in energy that produces sound. So what we do with sound is we work in terms of what are called decibels. So you've probably heard of these, and decibels are set up. We'll see the formulas here in a minute. What they do is they use a logarithmic scale. So what we find with human hearing is if the intensity goes up by a factor of 10 or a factor of 100, it doesn't sound 100 times louder. You know, hearing hearing works in a manner where you're hearing, you want to be able to hear really faint sounds, but when there's a lot of sounds around, you don't want to just be overwhelmed by all that sound. And so the hearing response that we have works that way. And so we can hear these really faint sounds. But if we hear something, now this is how much more intensity. The intensity increase here is a factor of 1 trillion. You know, it's 10 to the 12th times more intensity. There's 1 trillion times more energy than this faintest sound. And we experience that as being very, very loud, but it's not completely overwhelming. So, you know, we still manage something that's 1 trillion times more sound. So 0 decibels on this logarithmic scale is set at the threshold of hearing, at this 10 to the minus 12 watts per square meter. And then you can see as you move up through a whisper, you know, a conversation that looks like it's coming in at 60, 65 decibels. Here is a noisy restaurant, a busy street. By the time we get up to 120 decibels, we are at a loud rock concert, and we are what we're calling the threshold of pain. So I guess people attending a loud rock concert, the sound there is at the threshold of pain, I guess. Anyway, let's see how that works. Let's see how the decibels work. And I guess from the chart we can already take a quick look here. Notice that every time we go up by 10 decibels, notice we got a 10, 20, 30, 40, 50, 60, 70, 80, 90. Every time we go up by 10 decibels, the intensity has gone up by a factor of 10. And that's how logarithms work, right? If you add this much on to a logarithmic number, that number is actually going up by factors of 10. Let's take a quick look at this too. So the sensitivity is not uniform across all frequencies. Remember we said that human hearing, we can pick up sounds between 20 and 20,000 hertz in terms of frequencies. Now, this is the threshold of hearing. Notice that at these really low frequencies, we can only hear sounds that are higher than like 60 decibels. So this is the sound level. Here is the intensity in watts per square meter. This is being measured in decibels. This is being measured in watts per square meter. We really only get down to that 0, where is the 0 decibels? We really only get down to 0 decibels at around 1,000 hertz. Now, what this is showing is that we get a little beyond 1,000 hertz, between 1 and 5,000 hertz. Our hearing is actually better than 0 decibels. So again, this is a logarithmic scale, and that means that 0 decibels does not indicate that there's no sound at all. 0 intensity would say that there's no sound at all, but decibels work differently. So the 0 point just becomes a reference. Okay, here is the formula. So what we do is we take a base 10 logarithm of the intensity relative to our reference intensity. So that becomes I over I naught. And then we take the base 10 logarithm and then we multiply that by 10. Now, you might wonder the name decibels. Where does that come from? There are actually units called bells. A decibel is 1/10 of a bell. And so this factor of 10 outside makes them decibels. If it were not the factor of 10 outside, if it was just purely the base 10 logarithm of the intensity divided by the reference intensity, those are called bells. Okay, and putting a factor of 10 in front makes that 10 times as many, and so we call those decibels because they're smaller units. So we're going to use the symbol beta, the Greek letter beta, to represent sound loudness or sound level. And sound loudness or sound level in decibels, officially decibels are unitless. If you take a look at what we've got here, the I and the I naught have units of watts per square meter. But those cancel out because we're using a ratio. So there's no units here, and that's a good thing because we want to take a logarithm, and you can't really take logarithms of units. And so the units have already canceled out. And once we get to this side, there's no units left. So the decibels are, in some sense, artificial. They don't really carry any units with them. But this turns out to be really handy to describe how loud a sound is, how loud we will experience a sound to be. So let's say we're on a busy street and the sound level, the sound loudness, is at 75 decibels. What's the intensity? So, hey, we just used the formula that we were given, right? Now what's important in this formula is that reference intensity. So here is the formula. Now, this isn't set up the way we want because in the problem they gave us beta. They said this is 75 decibels and what we want to solve for is I. So let's flip the equation around. What we're going to do is take these, this formula, and what we'll do is we'll divide through by 10, bring the 10 over to one side, and then we'll do an exponentiation. So we'll remove the logarithm by exponentiating, and we're in base 10, so this exponentiation needs to be base 10. So first of all, we got the log of I over I naught is beta over 10, and then we'll exponentiate. This will become I is equal to I naught, 10 to the beta over 10. So that's the reverse equation, and that's just as important, right? That's going to show up just as frequently the formula here as this one. So make sure you're good with solving these problems in either direction. And you know, logarithms to me are one of those things where every time I run into logarithms, I have to kind of stop and remind myself what some of the algebraic rules are for using logarithms. Logarithms are a little tricky; they're a little hard to hold on to. So it's a good, opportunity. It's a good chance to go back and kind of review properties of logarithms. So now that we've got our formula, what we can do is I can plug in the 75 here, and then follow through with the calculations. Now make sure you know how to take 10 to some power on your calculator also. It may have been a while since you have done logarithm or exponential calculations using base 10. So base 10 is not the same thing as base e, I guess is what we're saying here. So beta was 75 decibels. That is, 7.5 bells is one way we could write that. But let's get back to the formula here. This is 10 to the 75 over 10. What that's going to give us is 7.5 powers of 10. I can think of this in terms of how many powers of 10 are we using here. And so at 75 decibels, I am 7.5 powers of 10 times the intensity at threshold. So here is the threshold intensity. This is going to get multiplied by 7.5 powers of 10. That worked out to be, 7 powers of 10 gives me 10 to the 7th. And then the question is, what's 10 to the 1/2? And that turns out to be 3.16. So I can plug all these in my calculator. I'm ending up with an intensity that's 3.16, 10 to the minus 5. I compare that with threshold intensity, and I can see that there are those 7 powers of 10 plus an additional amount. So when you're doing these calculations, stop and talk yourself through them, and kind of remind yourself how these logarithms are going to work. Here's another example using decibels and watts per square meter. It says that a high-quality speaker is advertised to be able to represent frequencies all the way from 30 hertz to 18,000 hertz. So I'm getting some kind of a speaker from my stereo system, and it's going to faithfully represent the sound level at all frequencies within 3 decibels, plus or minus 3 decibels. That's the variation from across the frequency spectrum for this speaker. Now, what does that mean? What does it mean to have something vary by 3 decibels? How much is the intensity varying in that case? So let's do this. Let's say I have 2 different frequencies, and at those frequencies I've got 2 different loudnesses. I've got loudness beta 1 and I have loudness beta 2. Now the difference between those, they're telling us the delta beta is 3 decibels. So let's just see how this formula plays out. How would the intensity vary, between I1 and I2 if beta 1 and beta 2 are different by 3 decibels? So what I'm going to do is I'm going to use a ratio. The way these work, because they're exponentiation, what we want to do is take a ratio of the 2 intensities. Now if I take the ratio of the 2 intensity formulas, the I naughts are going to cancel. So the I naughts will go away, and it says it no longer depends on my reference intensity, because now the comparison is between 2 different intensities. Now that cancels, and then when I've got these powers of 10, if I have a 10 to some power divided by 10 to some power, it's going to be this number subtract this number. That's going to become beta 2 minus beta 1 divided by 10. And so I can write this as the difference, the ratio of intensities, I1 and I2, is equal to 10 to the difference in loudnesses divided by 10. That's how it's going to work. And so at this point I go, well, I can put 3 in, because they said that the uncertainty in the loudness was going to vary by plus or minus 3 decibels. Now it did say plus or minus 3. Maybe we should put in 6. If some of the frequencies are 3 decibels louder and some of the frequencies are 3 decibels more quiet. In any case, plugging the 3 into here gives us 10 to the 3/10. And it works out just coincidentally that 10 to the 3/10 is almost exactly equal to 2. It's not exact, it's 1.995 something something something. But comes in very close to a factor of 2. So, I guess that's a handy thing to remember. A 3 decibel difference is about a factor of 2 in terms of intensity. Now you might be thinking, well, wait a minute, intensity factor of 2, that's enormous. If some of the frequencies this speaker is putting out are being represented at twice the intensity as other frequencies, but remember, our hearing isn't that sensitive to, the 3 decibels difference is not going to sound like twice as loud. It's going to sound much less than that. So it probably is manageable, this factor of 2 in terms of actual intensity. Now, to kind of show how these logarithms work, I put together a chart. So I said, well, this is an interesting problem. This is the one we just looked at. What I could do is I could plot the intensity ratio as a function of delta beta. So the difference between the sound levels, if I have a difference of sound level, and I did that on the horizontal axis from 0 to 10. So now the way that formula works is by the time the sound level has gone up by a factor of 10, the intensity has, not by a factor, I'm sorry, by the time we add on 10 decibels, the intensity has gone up by a factor of 10. Okay, so along that horizontal scale, what we're thinking is here's 1 more decibel, here's 1 more decibel, 1 more decibel. So adding 3 decibels to this exponential plot gives me a factor of 2. Well, adding 3 additional decibels gives me an additional factor of 2. Now I'm up to 4 times the intensity. So here we were at twice the intensity, here we're at 4 times. What would happen if I added 3 more decibels and went all the way up to an increase of 9? What if I had an increase of 9 decibels? Well, that would be a factor of 2 times 2 times 2. That would be 8 times the intensity. And you can see from the graph how that plays out. So again, I find myself doing this too, is with these logarithmic formulas, kind of staring at graphs like this and reminding myself how logarithms work. So I think this is probably a useful graph to think in terms of. Here's an interesting example. It says this. It says that we have some trumpeters. We have 3 trumpet players. They're each playing at a sound level of 75 decibels. So each trumpet individually is producing a sound level of 75 decibels. What will the combined decibel level be? Now, we can't just add them, right? Because decibels don't add that way. What we have to do is we have to add intensities. So what we're going to need to do is this. Let's take that 75 decibels and find out how much, what the intensity is for each one of those. Now I think we had looked at this earlier, right? So this goes back to the busy street corner. It was 75 decibels too, and now it's the trumpeter that is at 75 decibels. So now we've calculated this, and when we calculated this, we got 3.16 10 to the minus 5 watts per square meter. Now that's each trumpeter. So I'm going to take 3 trumpeters. If I got 3 trumpeters producing this much intensity, well, the intensities will add. And so I'm going to get a combined 9.49 10 to the minus 5 watts per square meter together, all 3 trumpeters together. Now that I have the intensities, now I can go back and use the formula to take that intensity and convert it back into a beta. So, and what I ended up with plugging into this formula was 79.8 decibels. So what I saw was an increase. What was it we started? We started at 75. And what we did, notice that the intensity went up by a factor of 3, and what that led to was an increase of 4.77 decibels. So that was it. It went from 75 up to roughly 80. So it went from 75 to 80 decibels. It only went up by 5 decibels. And that's how we perceive things. So think about that. If you were listening to one person speaking, maybe you're at some kind of gathering, and one person speaking, well, what happens, you're at some kind of gathering and there's several conversations going on. It doesn't sound 4 or 5 times as loud. It's harder to pick up individual conversations. But if 4 or 5 different conversations are going on in a room, it doesn't sound 4 or 5 times louder than one conversation. And that's just the way our hearing works. And what we can do with this problem too is we could go back. Let's see, this time, we had an intensity ratio of 3. So what I'm going to do is come over to this intensity ratio and go, okay, I'm going to come up to here. 3 is right there on my intensity ratio. What I'm going to do is I'm going to follow over and see how many decibels that would correspond to. And coming down here, I'm somewhere, not quite 5, but somewhere in that region. So again, I can take the intensity ratio that was 3, come over to here, drop down, and that, 4.77 seems reasonable from that graph. All right, now what happens if we have a central object, let's see, an increase in sound. Okay, this is kind of a follow-up from what we just talked about. Here's kind of this new question that's coming up here. What happens if the sound is spreading out in all directions? Up until now, we've kind of been treating this as if we're just immersed in some kind of a sound that has a certain intensity to it. But the intensity is going to drop off with distance. So as we get farther and farther away from the sound source, the intensity is going to drop off. It's not going to be as loud when we step farther away. So how can we manage that? Now here's a jet engine. So they're saying here that if you are 30 meters, now 30 meters is a pretty good distance away. It's not like this mechanic operator, this controller who is directing this jet plane is able to stand 30 meters away, maybe not. So if the sound level at 30 meters is 140 decibels, now 140 decibels, that's really, really high sound level. That's going to cause hearing damage, a continued exposure to something at 140 decibels. That's past the threshold of pain. What would the sound level be at 300 meters? That's 10 times as far away. And they're saying ignore reflections from the ground. So we're going to do a bit of an idealized calculation here. What we're going to say is this. Here's the sound source. In this problem, that's a jet engine. And then we're treating the sound as if it's spreading out uniformly in all directions. So I can think of that central source being surrounded by spherical shells. So here is a spherical surface located a distance from the source, R1, and here is another surface farther away. This is at a distance of R2. Now the intensity that we see it at location 1 is going to be the power of the source. How many watts of sound is that source producing? Divided by a spherical surface area. So if you remember, intensity is power per area, and the area in this case is the surface area of a sphere. So now the sound is spread over a spherical surface. Here it's spread over another spherical surface, but it's even larger. It's a much larger, possibly, spherical surface. And so what we can do is take these two equations and do another ratio. So I do a ratio of I2 over I1. When I take these formulas and take this ratio, the powers cancel out. So the power factor is gone. The 4 pi's cancel out. All I'm left with is a ratio of R1 squared over R2 squared. So all I need to know to calculate this, I don't really have to go back and calculate the power. I could. I probably should have. I think we did this in chapter 15. We could go back and calculate the power using this formula. But what we're going to do instead is we're going to calculate the intensity at location 2. That ratio we can get by taking the 30 meters divided by the 300 meters. Now, that was a factor of 10 increase in distance. And since the ratio of distances gets squared in this formula, that becomes 1 part in 100. So the sound intensity is only going to be 1/100th as loud. Now, if you remember, we can get the delta betas by taking 10 times the logarithm of a ratio of any two intensities. Now, if we do this, we don't have to work from the reference threshold of hearing. We can work in terms of whatever ratio we want. And when we do that, that's the logarithm of 1/100. Well, the logarithm of 1/100, that's going to be -2. That's -2 powers of 10. And so the difference in loudness is going to be 20 decibels. It's going to be 20 decibels not as loud. So what this is claiming is even at 300 meters away from this jet plane, we're still going to be at a sound level of 120 decibels, that's still a rock concert, right? So if you stand 300 meters away from the jet plane, it's a rock concert sound level, versus standing really close where you've got to have very, very good protective gear to protect your hearing at something like 140 decibels. Now, is this really going to happen? Are we still going to hear this sound? The sound gets absorbed. So sound does not, the energy that was associated with the sound, it becomes thermal energy. So that pattern of sound doesn't travel forever without some damping effects. So what's going to happen is there's going to be damping. Now, the damping effects happen over the distance of hundreds of meters. So at that 30-meter distance, not much damping has taken place. But by the time we're out to 300 meters, we could have lost a good portion of the intensity due to damping. Maybe half of the intensity has gone into thermal energy, which we're not going to pick up as sound. It's going to go back into random motion of the air molecules. So again, this is a bit of an idealized setup, assuming that the sounds will drop off like 1/r². It's actually, there's a dampening effect where they drop off exponentially over distances of hundreds and hundreds of meters. Now, there was a formula earlier on where we were looking at intensities, and we were looking at pressure differences, we were looking at displacements of air molecules. And what this is going back and using those formulas. Now that we've talked about intensities more, let's go back and find out just how much displacement, just how much pressure variation are we expecting for a particular intensity of sound. And so here it is. What we're going to do is, now the sound they've given us, this is in the problem, this is given. It says that what we're going to do is we're going to take sound at a frequency of 1,000 hertz at the threshold of hearing. So I got to go back to that chart that we looked at earlier. So here's the chart from before. And this is showing me that if I'm looking at frequencies at 1,000 hertz, the threshold of hearing is at 0 decibels. So that's what they're telling us, is to go ahead and use a loudness that is at 0 decibels. So let's try that. So now the threshold is at 0 decibels, and also on that very same chart, I could have just read this off. 1.0 10 to the minus 12 watts per square meter is the intensity that we're looking at. So if I have a sound that I can just barely hear, again, you're back at the doctor's office, they're checking out your hearing, and you can just barely make out that sound. That's an intensity of, let's say, 1 times 10 to the minus 12 watts per square meter. How much of an amplitude, a displacement amplitude, will we have for the air molecules at that intensity? So we derived this formula back in chapter 15. We're going to make use of this. We're going to solve for A. Now, for the speed of the wave, we're going to use the speed of sound. So the speed of sound that we looked at was 343 meters per second. That's what we're going to be using here. And this is the intensity. This is the density of air at 1 atmosphere, 20 degrees Celsius. And then this is the frequency in terms of radians. So the radians frequency squared, yeah, that's all the stuff that we have from this formula when we're solving for A squared. Now, I got to remember to take a square root. I know it's an easy thing to forget, but I'm going to calculate all these numbers, take a square root. It worked out to be 1.11 times 10 to the minus 11 meters, a lot of ones in there. That's the amplitude of displacement. That is saying that when we have this sound that we can just barely hear, the air molecules, compared with their normal distribution, have been compressed at most. You know, how much have they shifted to create this compression? And the amplitude is only about 11 picometers. That is tiny. You know, atoms, a typical molecule, air molecule, might be a few hundred picometers across. So what it's saying is that the air molecules have shifted much less than their size. So on average, you know, you get this random distribution of air molecules when there's no sound, when it's, you know, when it's perfectly quiet, you've got this random distribution of air molecules. And when the sound, this very faint sound comes through, the air molecules shift by a distance, you know, much smaller than their own diameter. Okay, doesn't take much to be able to set off hearing. Now, in terms of, I wanted to put a much louder sound in there. So I went up to 80 decibels. I said, what about 80 decibels? Where it's, you know, it's pretty loud. I'm outside and we're in traffic and a lot of sounds going on. At 80 decibels, the intensity goes up, well, by 10 to the 8th. That's the intensity goes up by a factor of 100 million. And so if we increase the intensity by a factor of 100 million, how much does the amplitude go up by? Well, it gets square rooted. So instead of an effect of 10 to the 8th more intensity, well, you get 10 to the 8th more intensity, but the amplitude goes up by 10 to the 4th. So that would give us an amplitude that is 10,000 times larger. So that amplitude worked out to be 111 nanometers, you know, still much smaller than you could measure. You can't see something that small, but it's much bigger now. You know, it's 10,000 times the amplitude that it was at threshold of hearing. And if you went up to that much louder rock concert sound, you know, that's going to go up by another factor of, intensity would go up by 10 to the 4th, amplitudes would go up another factor of 100. So the amplitudes vary a lot between really faint sounds and really loud sounds. Now we can use the intensity formula that we solved in terms of pressure variations, and so we can write that and use that to calculate how much of a pressure variation we would see. Now again, this is going back to the 0 decibel sound, and so what I have here is my threshold of hearing. I've got my 1.0, 10 to the minus 12 watts per square meter as an intensity. Here is the density of the air, and here is the speed of propagation of the sound disturbance. There's my square root sign. I remembered my square root sign. The variations in pressure that we're getting for this is 2.0, 10 to the minus 5 pascals. Now, atmospheric pressure, if you remember, is 100,000 pascals. So the background pressure is at 101,300 pascals. And when this very faint sound comes through, it's only shifting the pressure by 20 millionths of a pascal. Okay? That's not much. Okay? Now that's the really, really faint one. So again, what we could do is instead of using 0 decibels, instead of using threshold intensity, we could boost that up to 80 decibels. That's going to take the intensity and increase it by 100 million, 10 to the 8th. And so the delta pressure, the same as the amplitude, is going to go up by a factor of 10 to the 4th. So 10,000 times as much pressure. Now even with that, you know, quite loud sound, 80 decibels is going to be a pretty loud sound, we're still seeing pressure variations of less than 1 pascal out of 100,000 pascals. So these are tiny variations in displacement and in pressure. All right, let's see how we are looking here. We are going to take a look at sources of sound. We're going to start looking at some vibrating strings and air columns. So we're going to be looking at musical instruments. And it says here they produce sound in various ways. We've got vibrating strings, vibrating membranes, vibrating metal or wood shapes, vibrating air columns. Okay, here are all the variations of how we make sound. We make different noises that we kind of like to listen to. Now, what they've got here, this is a set of frequencies that we have set up for, think of this as a piano. So here is a note on the piano. This is what is referred to as middle C. So if you've looked at a piano, I mean, all of you probably are familiar with what a piano kind of looks like. There are the white keys and the black keys. And so if we start at what's called middle C, and then the next white key is D, and then E, and then F, G, A, B. And then in between some of these, we have the black keys, the C sharps, or D flat, D sharp, or E flat. So you can see what the names of these are. Now, what they're giving us here is a series of frequencies. Now, where are those frequencies coming from? What we do notice here, and what they're talking about over here, is notice that if I'm at middle C, the frequency is at 262. Well, what happens if I go back up to another C that's an octave higher? So, you know, if you've seen a piano keyboard, then you know that there's a repeating pattern. What happens is there is, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different keys that make up that pattern, and then the pattern repeats. And so we call this a C, we go through all of these notes, and then we get up to this pitch, and we start over calling that C again. So what's going on here? And it says this. It says that going from C here to C, the next C is considered to be an octave difference. That's an octave higher. Now, octave suggests 8 steps that would be taken here. Now, the steps that are taken here, if I start at middle C, then I skip the black keys in this case. I'm just counting the D, 2, 3, 4, 5, 6, 7, 8. So if I do C, D, I guess if this is easier. If I do A, B, C, D, E, F, G, that's 7 notes. So this idea of an octave is saying that I'm counting this C and I'm counting the next one, and there's 8 notes that I'm going to hit in a particular scale. But along the way, I'm skipping some of the notes. Clearly, it looks like the repeating pattern is 12 steps, and what we want to do is we want to make these steps somehow evenly spaced. So let's see how that's done. So, of course, these musical scales, just developed by musicians, somebody puts a string on a guitar or some kind of an instrument, plucks it, and decides, wow, that's a nice sound. And then they go, let's put some more strings on there, and tune them differently, and see what kind of sounds we can generate. And so the scale that we just showed before, the scale that shows up on like a piano, this octave doubles the frequency, but it doubles the frequency in what we call 12 half steps. So this time we're going to leave all the notes in. We're not going to leave any of the notes out. We're going to play them all, what's called a chromatic scale. And by the time we have gone through 12 of these half steps, we have doubled the frequency. Now, when we double the frequency, the pattern of sounds that are created by two pitches that differ by an octave, there's a close relationship between them. So what I've done is, instead of starting at middle C, I've actually started at the A, below middle C, and then I've listed all the frequencies up to the A beyond middle C. Now, you may, if you play musical instruments, you may know that often we tune to the A above middle C, and that's at 440 hertz. So officially, that's supposed to be 440 hertz. If you have a tuner app on your phone, for example, the default for that is going to be tuning A at 440 hertz. And then all these other frequencies follow from that. So where is this coming from? Well, we decided that we were going to take this doubling of frequency, divide it up into 12 what we call half steps. And if we're going to double the frequency, what we want to do that is come up with a factor. What we want to do is say that each frequency in our list is equal to the frequency just before it times some kind of factor. Now the factor I have listed here is 1.05946 something something something. Where is that coming from? And it's 2 to the 1/12th. So the official way of tuning a piano, for example, is to make sure that each note is higher in frequency from the one before it by a factor of 2 to the 1/12th. Why 2 to the 1/12th? Well, if I make sure that each half step increases by 2 to the 1/12th, by the time I've gone through 12 steps, that will give me a factor of 2. So 2 to the 1/12th works out to be this 1.05946 something something something. And if I take that number and I go through 12 half steps, that accumulated effect doubles my frequency. And this is what's referred to as the well-tempered scale. So now what happens here is, let's take a look. The A, officially, this A is at 440 hertz, and that says that this A, the one the octave below, has to be 1/2 of that in terms of frequency. So I started with this 220 here. So 220 is an A, and I took that factor and I multiplied consecutively by that factor, and then I rounded. So these are rounded. They don't come out to be exactly integer values. These are going to be come from using this 2 to the 1/12th. And so those are the pitches that I came up with. Now, within music, what we found is that if you have certain ratios between different pitches, between different frequencies, they produce certain sounds. And it does turn out that if you play different pitches in a ratio of 4 to 5 to 6 to 8, you create what we call a major chord. So if you guys have studied, if you've learned guitar or piano or something, and you've learned about major and minor chords, major chords have a specific integer ratio to them. Now if you'll notice, the A note here came in right at 220. The E came in at 330. Now it's not exactly 330, but it's pretty close. And so that particular ratio of 2 to 3 produces a certain sound. We call that a fifth interval between those two. a ratio of 2 to 3. And then certainly the 440 and the 330 and the 220 together produce produce a particular sound that, for whatever reason, has become very common in music. So music makes a lot of use of that. So there are these certain ratios that show up in these pitches. Okay, let's take a look at some instruments. And so let's start with some strings. Strings are maybe the easiest ones to think about. Now, in chapter 15, we looked at strings. We looked at what we called standing waves. And so all these musical instruments, what we're going to be finding is that there are standing waves that set up in the musical instrument in some way. And then the waves that are the oscillations that are taking place in those standing waves get propagated through the air, and we hear them. And so for this string is going to go into vibrations. Now, if you remember from chapter 15, there's not 3 strings attached here. What we've got is, this is the string when the string is at rest. So when it's not setting up any kind of a standing, when there's no standing wave present, this is what the string looks like. And then when there is a standing wave present, the string is oscillating back and forth. And we said this is a standing wave, and we showed mathematically that a standing wave is equivalent to 2 traveling waves of the same frequency, same wavelength, same wave speed, traveling in opposite directions. And so we actually do talk about these standing waves as having a wave speed to them. Now, this was what we called the first harmonic. And then we said that you can also, surprisingly, set up higher harmonic, second harmonic, third harmonic, where we have these nodes that show up at intermediate locations. And there's nothing, we're not reaching in there and holding the string to create that node. The string is creating that node all by itself. And that has to do with the way that the forces are set up, the tension is set up along the string, a point right in the middle here. If we're vibrating in the second harmonic, that point in the middle is going to not move. We're just going to set up a node at that location. When we move on to the third harmonic, that is a pattern where we have a couple of nodes set up. So here's a node on this end, there's a node on the other end, here is an intermediate node, here's an intermediate node here. So these different harmonics can be set up on a string instrument. So this could be a piano, could be a violin, could be a guitar, something like that. Now, if you remember, we had gone through, here's a guitar, and so what we can do here now is we can, on a guitar, when the guitar is being played, so here is a string, and they've kind of exaggerated the vibrations taking place here. This is a certain length string all by itself, but when the person is playing the guitar, they hold down the string at some location, and when they're strumming this part, it's shorter. So while they're playing the guitar, they're going to take each one of the individual strings, and you can change their lengths. So what you're doing when you move your, when you hold down, when you move your hand around and hold down different strings on different frets, you're creating different lengths for each of those strings, and then when you strum them all, you're going to end up with different frequencies. You're going to end up with a different combination of pitches from those. All right, here's kind of a here's a good example to start with. Let's take an individual piano string, and it says that if we look at the highest key on a piano, that corresponds to a frequency that's about 100 times higher than the frequency of the lowest key. So you got this lowest key, you got this highest key, and that's a difference in frequency of about 150. So it says this. It says if we use a string for the highest note to be 5 centimeters, so that's going to be a really short string. what would the length of the string need to be for the lowest note if all the strings are the same density and all the strings are under the same tension. So here we go. Let's take a look at a piano. Now the lowest note on the piano, a standard keyboard, is called A naught. It's at 27.5 hertz. And the A above that, one octave above, is at 55, another octave 110, another octave 220. Here is A4. This is what we said is kind of standard reference tuning pitch. And that is the 4 octaves above the lowest note. And that's at 440. And then we can continue. What happens is we have 3 additional octaves of A, which put us at 3,520 hertz. And then there's just a couple notes beyond that. There's the B flat, the B, and then the C. Now that C is actually referred to as C8. It seems like it should be C7, but they change the numbers when you get to a C. In any case, that highest pitch on the piano, official tuning, 4,186 hertz. So the piano is set up to create frequencies between 27.5 and 4,186. How's that going to affect the lengths of the string? Well, what we found with the lengths is this. If I have a string set up and we're in the first harmonic, so for all of these, we're only considering the first harmonic. What we find is that the wavelength of that first harmonic is 2 times L. The frequency is given by speed of the wave over that wavelength. Now, the speed of the wave, it depends on the tension and the density of the string, and then we have to square root it. Now, what we decided with this is, well, for this particular example, let's treat it as if we're going to build a piano. All the strings are going to have the same thickness. All of the strings are going to have the same density to them, and that means that they're all going to have the same wave speed. So that says the first harmonics are going to be given by that wave speed, which we're treating as a constant, divided through by 2L. Now, that says that if I want the frequency to go up by roughly a factor of 150, I would need the length to increase. Or if I want the frequency to go down by 150, I have to make the length go up by 150. So at that highest frequency, that's 4,186 hertz. Now we don't know what the speed of the wave is because we don't know how much tension is on those strings, and we don't know what the strings, how thick they are, and what they're made out of. So we don't have individual numbers for these values, but what we were told is that they're all the same strings, the same string material. They've all been tuned to the same tension, so they'll all have the same wave speed. So using ratios, it says that I would need to have the length increase by a factor of 150 in order to have the frequency go down by 150. That would make for a really big piano, because if that first string is at just 5 centimeters, right? It's a very short string. If I multiply that by 150, that gives me 750 centimeters. That would give me a piano with a length of 7.5 meters. That would be like all the way across the room here, right? So that would be an enormous, that would be a really grand piano. It would be a grand piano at 7.5. So of course, what happens instead is to get lower pitches versus higher pitches, what we want to do for the higher pitches is use strings that have a lower density to them, and to get the lower pitches, we want to get strings that they're heavier. They have a larger value of mu. So if you look inside a piano, or if you look on a guitar, you can see that the strings are not uniform thickness. The heavier strings are being used to give us a lower wave speed and a lower frequency. The thinner strings are giving us, the lower mass strings are giving us higher wave speeds and higher frequencies. Okay, I think we're out of time, so I think we're going to stop there, and then we'll pick up with the rest of the chapter. If you guys have questions, stop by.